Deep beneath the border of France and Switzerland, the Atlas detector at CERN waited in silence, surrounded by layers of concrete and steel, humming with anticipation. For years, it had been the silent witness to the universe's most secretive conversations, listening for whispers in the dark. It was just after midnight on July 3, 2025. The world above slept, unaware that something extraordinary was about to unfold far below their feet. The Large Hadron Collider had been smashing protons together for months, monitored by a handful of physicists in a dimly lit control room. The air was thick with the quiet tension of routine, punctuated only by the soft hum of computers and the occasional murmur of conversation. Suddenly, a data plot appeared, 3 perfect laser-straight lines radiating from a single point. The image was so clean, so precise, it seemed almost artificial. The junior physicist's heart pounded. 3 muon tracks, not 2, not 4, 3. It was as if the universe had paused just for a moment to deliver a message directly to them. The standard model of physics said this was impossible. Every textbook, every lecture, every simulation had insisted 3 muons from a single collision simply could not happen. Disbelief swept the room. Was it a glitch? Diagnostics said no. The detector was flawless. Every system check came back green, every safeguard in place. Supervisors gathered, faces tense with awe and confusion. The weight of the moment pressed down on everyone present as if the air itself had thickened. The event was quickly nicknamed the 3-Eye event. The name spread through the lab like wildfire, whispered in hushed tones as scientists tried to process what they were seeing. It was a singular, pristine anomaly, a message from the universe in a language we didn't understand. The data defied every expectation, every prediction. The data was crystal clear, the signature unmistakable, there was no room for doubt, no statistical noise to hide behind. On that quiet night, a small group of humans witnessed something that would force us to question the very foundations of reality. The boundaries of known science had been breached, and there was no going back. This was not a subtle hint or a statistical wobble. It was a thunderclap, a cosmic exclamation point that demanded attention. The search for answers had just begun. Theories would be rewritten, experiments reimagined, and debates would rage for years to come. The journey ahead would be more thrilling and more terrifying than anyone could have imagined. In that instant, the universe had blinked and humanity was forever changed. To grasp why this event shook the scientific world, picture the Large Hadron Collider, a 27-kilometer underground ring where protons race at nearly the speed of light. Powerful magnets guide these protons, accelerating them to energies unmatched by any other machine. At key points, the beams collide head-on, unleashing showers of exotic particles. The LHC is a discovery engine, recreating the conditions just after the Big Bang. Our best guide, the standard model, describes 17 fundamental particles and their interactions, but it's incomplete. It can't explain gravity, dark matter, or dark energy. So, physicists use the LHC to search for new particles, forces, or even dimensions. Each collision is a roll of the cosmic dice, a chance to glimpse something never seen before. Sometimes the universe surprises us in ways we never expected. Atlas is a colossal layered detector, a digital camera for particle collisions. When protons collide, Atlas tracks the resulting spray of particles, measuring their energy and identity. The inner layers track charged particles, calorimeters measure energy. The outer muon spectrometer catches muons, which can punch through dense material. Most collisions produce chaotic sprays, hundreds of particles, mostly common types. Occasionally we see a pair of muons, as predicted by the standard model. These pairs are rare but expected, always produced in even numbers due to conservation laws. Physicists are trained to spot these familiar patterns. The detector also checks for missing energy, usually explained by invisible neutrinos. This is the normal world of particle physics at the LHC. Patterns are familiar, the rules well understood, until something breaks them. The 3-Eye event shattered those rules. In a field where every anomaly is scrutinized, this event stood out as something truly extraordinary, something that simply didn't fit into any known pattern. Instead of chaos, there were just 3 straight high-energy muon tracks, no ambiguity, no confusion. The tracks were so clean and distinct that even the most skeptical physicists couldn't dismiss them as noise or error. In the standard model, muons are created in pairs, not threes. This is a fundamental rule, as basic as the conservation of energy or charge. Seeing 3 was like watching gravity run backwards, a direct violation of nature's rulebook. It was as if the universe had decided, just for a moment, to ignore its own laws. The energy was even stranger. A massive chunk, 1.8 tera-electron volts, was missing. That's an enormous amount, enough to suggest something big was hiding in the data. That's not a small error. It's a gaping hole, far beyond what neutrinos could explain. The missing energy was so significant that it pointed to the presence of something entirely new. The only explanation, an unknown parent particle decayed, producing 3 muons and something massive, neutral, and invisible. Whatever it was, it left no trace except for the energy it carried away. This combination, 3 muons and huge missing energy, had never been predicted or observed. It was a scenario that no theory had ever prepared us for. It was a signature with no place in our understanding of the universe. The equations simply didn't add up, and the data defied every expectation. The event was not just odd, it was unprecedented. Nothing in decades of particle physics had prepared the scientific community for this. Physicists were left with a puzzle that defied every known law. Theories were questioned, and debates raged late into the night. The data was clear, the implications staggering. It was as if the universe had handed us a riddle with no solution. It was as if the universe had revealed a secret, then slammed the door shut. The sense of mystery was overwhelming. The 3i event was a message. Our rulebook was incomplete. The boundaries of physics had just been redrawn, and no one knew what lay beyond. The search for an explanation had begun. Teams mobilized, data was re-examined, and new theories began to take shape, and nothing would ever be the same. The 3i event had changed the course of particle physics forever, opening a door to mysteries we had never even imagined. In particle physics, the first question is always, could this be a fluke? We use sigma to measure confidence. A 5 sigma result is discovery level, with odds of a fluke at 1 in 3.5 million. The 3i event, 7.5 sigma, the odds of a random fluctuation, 1 in 300 trillion. The signal was too clean, too precise, too significant to dismiss. It was real. The standard model wasn't just incomplete, it was wrong in a way no one had anticipated. This wasn't a new particle that fit the old framework, it was something that broke the framework itself. Once the event was confirmed, theorists scrambled for explanations. Supersymmetry? No variant predicted 3 muons and this much missing energy. Extra dimensions? The models didn't fit the signature. Dark photons or hidden forces? Intriguing, but none could reproduce the clean 3 muon result without other unobserved effects. Every theory failed. The 3i event was an orphan, no theoretical family to claim it. It wasn't just another puzzle piece, it was from a different puzzle entirely. The textbooks weren't missing a chapter, they might need a new table of contents. For physicists, this was both thrilling and frustrating. We were off the map, in uncharted territory. The event demanded new ideas, new principles. The universe had thrown down a gauntlet, and we had no choice but to pick it up. As if the event itself wasn't strange enough, one final detail emerged that left even the most seasoned scientists in awe. The 3 muon tracks and the missing energy were perfectly balanced, aligned along the Earth-Sun axis, pointing directly at the Sun. This wasn't just a random orientation, it was as if the universe itself had drawn a line, connecting our planet to our star through this mysterious event. Coincidence? Statistically possible, but in the context of a law-breaking event, it felt like a clue. The odds of such a perfect alignment happening by chance are astronomically small, making the event even more tantalizing for those searching for meaning in the data. The 3i event has never been reproduced. Despite years of searching and countless experiments, no one has seen anything quite like it again. It may require conditions so rare we won't see it again until a more powerful collider is built, or perhaps until we develop entirely new ways of probing the universe's deepest secrets. Until then, this single perfect event remains our only clue, a tantalizing hint that there's more to discover, waiting just beyond our current reach. Why should anyone care? Because it challenges our most basic understanding of reality. It forces us to question what we think we know about the universe and our place within it. What is the universe made of? What rules govern existence? Are there forces or particles we have yet to imagine, waiting to be discovered? This event is a crack in our knowledge, a new light shining through. It's a reminder that the universe still holds secrets, and that every mystery is an opportunity for discovery. It's more than a new particle, it's a cosmic invitation to explore, to push the boundaries of human curiosity and imagination. The universe is stranger and grander than we ever imagined, filled with wonders that challenge our understanding at every turn. And the journey to understand it belongs to all of us, a shared adventure that connects every curious mind across the globe.